Hi, and welcome to our ninth session where we'll cover repeated measures and longitudinal data analysis in our first of two sessions on the topic. We'll start with identifying and defining hierarchical and longitudinal data, and then do an initial analysis of correlated data using analysis of variance before we'll go on in the next session to cover better methods. We'll define and calculate interclass correlation and identify and define random and fixed effects. We're starting with just the first section of your textbook today, and we'll continue with Chapter 7 in the next session. So after a brief introduction, we'll start with an example and then go on to interclass correlation and random and fixed effects in the context of this example. So what are hierarchical and longitudinal data? Here are some examples. Knee radiographs that are taken yearly in order to understand the onset of arthritis. So these are longitudinal because we have multiple measurements taken over a period of time on the same participants. Second example, an indicator of heart damage is measured at 1, 3, and 6 days following a brain hemorrhage. So that's again a longitudinal type of data with multiple time points measured on each individual. A third example, a group of patients in a urinary incontinence trial who are assembled from different treatment centers. So this is not longitudinal, but it's hierarchical because we have patients that are grouped together by treatment center. Fourth, susceptibility to tuberculosis measured in family members. Again, hierarchical because we have individual participants organized or grouped by family. And finally, a study of the choice of type of surgery to treat a brain aneurysm, either by clipping the base of the aneurysm or implanting a small coil, where the study is conducted by measuring the type of surgery a patient receives from a number of surgeons at a number of different institutions. So a lot of text here, but this is hierarchical with actually a couple of levels because we have patients grouped by the surgeon who operated on them, who are then in turn grouped by the institution where they work. So what is the distinction between hierarchical and longitudinal data? Well, really the only distinction that we make here is that longitudinal data are measures over time, but that is a type of hierarchical data in that we have repeated measures on the same unit over time. So in the examples that we had of hierarchical data, we had non-time related grouping, such as patients within a surgeons within a hospital, and in the longitudinal examples, we were talking about measurements of individuals over time. But as we've pointed out, other kinds of non-longitudinal data can also be hierarchical. So as a definition, hierarchical data are those data, whether it is responses or predictors that are collected from collected from or specific to different levels within a study. So by levels, we can be talking about time points within a patient, where time point is one level, patient is one level, surgeon is another level, hospital is another level, meaning that there are different levels where the data are organized. So why are these data special? Well, for starters, the outcomes are correlated across observations, meaning that that observations that are grouped within one group of this hierarchy tend to have something in common. They're not independent like we've been assuming for analyses so far in this course. And second, the predictor variables can be associated with different levels of hierarchy. So for example, we might be interested in the volume of operations at a hospital, whether that hospital is for-profit or not for-profit, so that it is a covariate or a predictor at one level of the hierarchy that applies to everything below that level of the hierarchy in the data. Another example, years of experience of the surgeon or where the surgeons were trained. So that's a covariate existing then at a lower level of this hierarchy. Or how the choice of surgery depends on age and gender of the patient. So these are two things at the hospital level, two covariates predictors at the hospital level, one at the surgeon level, and then a couple examples at the patient level. Okay, let's go into an example with some more detail. So the topic of this example is a condition where lack of digestive enzymes in the intestine can cause bowel absorption problems, which are indicated or measured by excess fat in the feces. There is a treatment, pancreatic enzyme supplements, that can alleviate the problem, and we have a data set for this, which is in with the lecture materials, fecfat.csv, which is the fecal fat quantity in grams per day for individuals given each of a placebo and 3 types of pills. So I call this repeated measures and not longitudinal because it's not measurements over time, but with each individual given 3 different treatments, either placebo, none, or a tablet, a capsule, or a coated tablet. So these aren't necessarily done in a particular order, so it's not time, it's just these 4 different treatments given to each of 6 different individuals. So it's a very small, simple data set. We just have 6 subjects and 4 different measurements per subject. And this table shows the marginal averages over pill type and subjects. So just very briefly looking at it here, we can see that across the pill types there are certainly some differences in the mean. The amount of fecal fat excreted for the placebo is about twice as much as for a couple of the different treatments. So we're going to follow up on this and see if this does in fact appear to be a significantly statistically significant improvement in the reduction of fecal fat. But looking at the subjects, we also notice here that there's a big difference in the average fecal fat secretion per subject, varying from as small as 6 grams per day, averaged across all treatments for subject 4, to as high as 47. So this starts to get at why here this hierarchy is important, in that we have clearly, so when I talked about there being correlated measurements, this is what I was talking about, how the grouping of the subjects matters. These are not just random observations across all of the subjects. They are certainly grouped by subject. Here's a box plot of these data. So this is sort of a non-hierarchical look at these. This is just a box plot showing the measurements for each of these 4 treatments. So you can see the 6 observations for each treatment, and you can see that for these 2, the tablet and the capsule, the average fecal fat secretion does look smaller than for these other 2, but you can't see here that some of these observations are on the same data. You can't see the grouping by patient and which of these points are measurements from the same patient. So how will we analyze these data? If we were to go back to your Biostat 1 methods, or methods from this course from before hierarchical data analysis, you might do it this way. So this is just an analysis of variance. So I'm fitting a linear model with fecal fat as the response and pill type as the predictor. So this is just an ordinary linear model that we have done when we had the assumption that each of our observations was independent. This is incorrect in this case because these fecal fat observations are not independent. The four measurements on each individual are correlated with each other. But if we go ahead and do it, we can get something that looks like an analysis of variance table. And if we do the F-test on there, we see that actually, so there's an F value of 1.886, p-value of 0.17. The difference in means across these four groups is not significant. However, this analysis does not count for that similarity of measurements within an individual. It would only be correct if each treatment were given to a different individual. So we had 4 treatments. If each individual received only one treatment, so we had 24 different individuals in this study instead of 6, then this would be a correct analysis. So another approach that you could take, which is getting closer, is a two-way analysis of variance where it accounts not only for treatment but for individuals. So it would fit a coefficient for mean fecal fat for each individual. And just to give you a visual idea of what that looks like, this spaghetti plot here is a plot of the measurements for each individual across the 4 treatments. And you can see here in a way that you couldn't see in the box plot that for this individual with the dashed line, there is a big reduction for the tablet and capsule, and then not so much reduction for the coated tablet. And you have this sort of U-shaped pattern across most of the patients. So you can start to see that there is a pattern that would not be visible if you don't look at this grouping by patients. So this approach of the two-way analysis of variance is equivalent to just subtracting the mean for each individual. So adjusting the observations so that they each have the same overall mean measurement for fecal fat excretion. So it's centered on 0 here now instead of about 40. So let's compare that. Here, this one way is the one that I showed you already. And now in this two way, I've just added another term, this subject term to it. So we have another line in the analysis of variance table. And look what has happened. Now, both of these p-values in this table are extremely significant. So by doing something to account for the subject effect, we actually are seeing that there's much better evidence of effectiveness of the treatment. So what happened? You often assume that by doing an incorrect analysis, you might see an effect that's actually no effect, like an artifact. But it's sort of in reverse here. By doing an incorrect one-way analysis of variance, we missed a statistical significance that does seem to be present. So what happened? Well, one-way ANOVA correctly estimates the effect of pill type. So the differences in average fecal fat excretion between the different pill types, that's fine, but what it fails to accommodate is this correlation within subjects. And so what happens is it overestimates the residual variance. All of the difference between individuals, it includes in the residual variance term, which increases the denominator of the F statistic and gives us a non-significant result and underestimates the significance of pill type. So let's now step back and look at what these models are that we've fit. We're calling for an ordinary multiple linear regression in this GLM framework that we've done. We're modeling the expected value of the outcome conditional on the predictors X according to this linear predictor. And there's no link function here, or it's just the identity link function. And in this particular example, we fit this two different ways. The first one is the outcome, the fecal fat measurement for person I with pill type J is an overall mean plus an effective pill type. So this is the overall intercept plus an effective of pill type plus the residuals. And then when we went to the 2A ANOVA, we still have this overall intercept, but we've added a mean per subject. So the outcome is modeled as the overall mean plus the subject effect plus the pill type effect plus the residuals. Now you can see how these residuals are really something different between these two models. In the first model, the portions of the fecal fat were explained by this overall mean and pill type with everything else assigned to residual variance or to error. Whereas here we have subject type split out as well. So everything that in the 2A ANOVA is explained by subject type, and residuals was all in the residuals. So what we assigned to subject in the 2A ANOVA was previously assigned to residuals. Now with all linear models, or with the analysis of variance, our ordinary linear modeling before we got into generalized linear models, we assumed this for the residuals, that is, and they were independently identically distributed with mean zero and a standard variance. And in this case, we can clearly see that these residuals are not going to meet this independent assumption on the residuals because we have subject mixed in. So everywhere where I is the same subject, these residuals are not independent. Here we're doing better. We are at least taking away the subject effect and the pill type mean. So it's still not a guarantee that these residuals are completely independent, but they're certainly closer than they were in the one-way ANOVA. So the one-way ANOVA failed badly because it didn't account at all for the correlation of measurements within person. That is how the amount of the outcome variable fecal fat varies on average from one person to another. And that raises the question of how can we measure that? How highly correlated are the measurements on the same person? So that is, when we go from one person to another, how much do all of the measurements on average change? So considering subject I, pill types J and K, we're writing out here just a definition of correlation. So what this is a Pearson correlation between the measurement on subject I between two different pill types. So on that first table that we saw where we had, here I'll put on my video so I can draw, where we had rows corresponding to each in subject and columns for each pill type. This is just the correlation between two of those columns. And this is a definition of correlation. It's the covariance of those two variables divided by the standard deviation of one times the standard deviation of the other. And this is a measure of how large this subject effect is in relation to the error term. So you can imagine if you have a large subject effect, that is where the difference from one person to another is much larger than any other effect, then this will be a very high correlation. We're going to go through a rare derivation in this class and just go ahead and calculate that correlation that I showed on the last page. Starting with the covariance term, remember I was the subject, J was, I think, pill type. Yes, J and K are both pill types. So this covariance can be simplified out to just the effects of subject I, and that's because the overall mean and the pill type are being modeled here as constants. That is, they are fixed effects, so they don't enter in. Covariance between a variable, any random variable, and itself is just the variance, and this is just another way of writing the variance. In this analysis with the two-way analysis of variance, subject was a term in that linear model, a fixed effect. And every subject has its own coefficient beta, and this is what we're used to. In the next lecture, our final lecture, we will change this and actually treat the effect of subject as a random variable, but we're not going to get to that yet. So the previous slide, we calculated the covariance that was the numerator of that Pearson correlation equation, and now we need the variance for the denominator. You recall the denominator was the standard deviation of the first variable times the standard deviation of the second variable. And these standard deviations we assume are the same. That was the heteroscedasticity assumption, so it's just one variance. And the difference here is that in the variance, the residuals actually do count. So we can break that up into the variance of the subject variables times the variance of the residuals. And just write this out as squares of standard deviation. So we've just broken down this variance of our outcome variable into subject variance plus residual variance. So this correlation calculation that I've just walked you through actually has a name that you will hear anytime you are probably reading the literature on a hierarchical data analysis, called intraclass correlation. And all it is the correlation between the random variables for two nested or hierarchical measurements. So in this case, treatments J and K across subject I, so just a single level of nesting here. So this correlation, where the numerator, the covariance, is this the subject variance, so this is the top level of the hierarchy, divided by the variance, which is broken up into the subject and the residual variance, is called the interclass correlation. And you may also see this written instead as tau instead of sigma, and tau 0 for the subject, or group level variation, and epsilon for the residual variation. Now, if you take just calculate the variance of this subject average, and this is actually just taking this column of means, calculating the standard deviation and squaring it, or calculating the variance, you get this value 279.4. That's actually increased quite a bit by the correlation of measurements within individual. Why is that this would be increased? Well, you remember that for independent measurements, the mean was given by the central limit theorem. It was always, or the variance of an average was, let's see, the standard deviation was equal to the individual standard deviation divided by the square root of the sample size. But that's under the assumption of independence. And when these are not independent, if you imagined that these were all perfectly 100% correlated, then this variance would actually just be the individual variance instead of being divided by the square root of the mean. So that would be the maximum. Now, in our case, you can estimate this by hand. This is kind of annoying and not something you usually will have to do yourself. But if you do, an easy way to do it from your two-way ANOVA, it's going to be easier once you learn the how to fit a mixed or a random effects model, because you will get these variance estimates just out of the model. But doing it manually, we actually have to make a little correction to this subject variance, and that is the amount that could be attributed to individual residual variance. And this is just the variance of the residuals and then divided by 4 to give us 1/4 for one of the columns. And you subtract this to get the variance of subject I, and then just use directly this. This is just a calculation of variance for the residual variance. So we have these two values, 252 and 106. And we can plug this into that ICC calculation. So that 253 was the slightly corrected subject variance, and the 107 was the residual variance. It gives us an ICC of 0.7. So this is the do-it-yourself way. But it's valuable just to look at this and think, okay, if all of my variance was due to subjects, and there was actually no variability between pill types here, then we would have 100% ICC. So that is, you just get the same measurement across a subject. So all of your measurements for one of the subjects are the same. That would be 100%, or an ICC of 1. Whereas if the residual variance is much, much larger than the subject variance, that all of the subjects have the same baseline, then that would be an ICC of 0, and the actual independent measurements within a subject. So I keep promising this calculation will become easier when you learn to estimate random coefficients directly in the regression model. But before we do that, I want to introduce the concepts of random and fixed effects to you. The two-way ANOVA that we fit today is what we call a fixed effects model. It looks something like this. This is what you are familiar with these a coefficient for each subject and a coefficient for each pill type. There's nothing new here. Now, in the mixed effects or in a random effects model, we're going to replace one of these terms, the subject coefficients, with, instead of coefficients, a random variable. So we will instead assume that the mean amount of excreted fecal fat is an overall mean plus a subject specific intercept. So that means that if you were to look at the mean across our 6 different subjects, there would be a distribution of means. And we're going to assume that that distribution is normal for the purpose of this random effects model. So it's a normal distribution with mean 0 and a standard deviation given by this subject-specific variance. So you can see that with a mean 0 for this subject random variable added to a mean, an overall mean, this gives us an overall mean of mu with a variance of mean fecal fat excreted given by this sigma squared subject. And then the other parts stay the same. This is a fixed effect for pill type plus our residuals. So I called this a mixed effects model because we have a fixed effect of pill type, meaning that the effect of, say, a capsule is the same for everyone. That is not a random variable. We assume that in the population, say, taking a capsule instead of the placebo has some fixed fixed change in fecal fat excreted on everyone, or at least on everyone that has the same set of covariates. We could have an interaction term or something, but this effect is assumed in the population not to be random. Whereas this subject effect now is assumed to be random in the population. If we were to increase ourselves to an infinite sample size, we would get down to a perfect measurement of pill type, but we would always see we would see a normal curve of mean fecal fat excreted across all pill types for each individual. So this is called also a random intercept model because we are assuming that the intercept, the mean amount, the mean per individual is random. It is possible to also have a random coefficient of pill type. So rather than assuming that the effect of taking a capsule is the same for everyone, to assume that the effect of taking a capsule is also a random variable. But that's not what this particular model is showing. So the book provides this little decision tree for deciding between fixed and random effects. I don't know how useful this tree really is, but the key thing is to ask yourself, are the levels of a factor, or is the thing that you're trying to estimate, is it a fixed value or does it come from a probability distribution? So in the case of the baseline amount of fecal fat excreted in that example, if that were something that that we wanted to assume was constant in the population and just took one value, that would be a fixed effect. But if we're assuming that it comes from a probability distribution, so say there is a population mean and a standard deviation, so it's a random distribution, then it's a random variable. And with the effect of pill type, if we were comfortable with assuming that the effect of, say, taking a capsule instead of the placebo was fixed and the same for everyone, then that would be a fixed variable. But if that effect of pill type instead is something that also varies randomly in the population, say has a mean and a standard deviation, then we would treat it as a random variable or a random coefficient. So this next tree, where does the interest lie? Well, it could be just in the distribution of the random effects, or in the distribution and the realized values of the random effect, meaning the actual effectiveness of the treatment on individual persons. In either case, we're going to have to estimate parameters of the distribution of the random effect. So say if under the assumption of a normal random effect, its mean and its standard deviation. I'm not sure why there's a decision tree here when this is the same for both. To summarize, subject-to-subject variability, that is when we have multiple measurements for each subject, it simultaneously raises or lowers all the observations on that subject, and that induces a correlation on those within subject measurements because they are varying up and down together. And then we broke up this variability of individual measurements into two parts, into the part due to subject variance and into residual variance. And then we used the 2A ANOVA to get at these estimates, even though it didn't directly estimate variable due to the subject. So we used the variance of the coefficients and then had to make a little correction for the amount of individual variance that was in there. I pointed out that the estimates for the coefficients, that is the effect sizes or the changes in the mean, in this case of fecal fat excretion induced by the different enzyme delivery modes, was unchanged by hierarchical modeling. It's just the size of the residuals that was changed. And we saw that this had a big effect on the residual variance, F statistics, and p-values. And in this case, it was conservative. We got a p-value that was too large by ignoring the within subject correlations, but that is not always the case. It can be the other way as well, where you get p-values that are too small. We introduced this measurement, the interclass correlation, to provide some measure of the amount of the importance of the grouping, that is the amount of correlation induced on measurements by those groups. And we introduced fixed and random effects, which you will be modeling in our next session. Thank you.